Hey everyone, in this video we're going to learn how to solve projectile motion word problems. These problems are going to involve throwing or launching an object up into the air and measuring the height above the ground in relation to time. Our first example, a ball is launched straight up into the air from the edge of a 96-foot cliff. The height of the ball above the ground is modeled by h of t equals negative 16t squared plus 16t plus 96, where t is measured in seconds. The graph is shown below. So we have a quadratic function, we have that t squared term. Our graph is a parabolic curve, as we can see here. Now, one thing that's important to understand, this parabolic curve, this graph, does not represent the path of the ball. It's not that the cliff is right here and the ball is being thrown off the cliff and then it's going to land down here. The reason that's not the case is the x-axis is time, okay, not distance away from the cliff. The path of the ball, what that really looks like, so the ball's here, it's thrown straight up in the air, then it's going to stop, and then it's going to come back down. So if we were measuring, so let's say right there, that's t equals 0. And then it gets to that highest point. Let's try to base it off this. So that looks at about 1/2, right? So it gets to that maximum point at t equals 1/2. Then it starts to come back down right here at t equals 1. And then t equals 2, it's a little bit closer to the ground. And then t equals 3, it's back at the ground. So if we took each of these points with the t values and the appropriate height, and we plotted them, this is what the graph is going to look like. These would be those blue points. Okay, so that's an important understanding that the ball's being thrown straight up and down. This graph represents the height of that ball in relation to the ground with respect to time. Now let's look at a few of the critical points that we've been graphing with our quadratic functions. So the first one, let's look at that vertex. That vertex is the turning point of the curve. That's the point at which the ball is the highest off the ground. We can see that in our little diagram here as well. Well, we know how to find that, right? Axis of symmetry, that would tell us when it's going to happen. And then if we plug that value into the function, we would get the y value, which is the height. Here, the y-intercept, that's going to be the initial height. How high off the ground is the ball starting? And then we get all the way here to the x-intercept. Well, that's the point where the ball hits the ground, right? Where that height is 0. So all those critical points that we've been finding can now be applied to these projectile motion problems. So now let's take an algebraic approach to answering all those questions. So same setup. What is the height of the ball after 1 second? So we're going to evaluate the function at 1. So h of 1 is negative 16 times 1 squared plus 16 times 1 plus 96. So 1 squared is 1. So we have negative 16 times positive 1 plus 16 plus 96. So that's going to be negative 16 plus 16, which is 0, plus 96, which is 96. So 96 feet. That will be the height off the ground after 1 second. When does the ball reach its maximum height? Well, as we said, that's that vertex, right? The turning point of the parabolic curve. Okay, so the first thing we need to find to answer this question is the axis of symmetry. Right, the axis of symmetry, just to sketch the graph again, the axis of symmetry tells us when that ball is at its maximum height. So instead of x equals, we're going to use t equals, because that's the variable in the function, still negative b over 2a. So we have t equals negative 16 over 2 times negative 16. So we can simplify the negative 16s, put a 1 in the numerator, so t equals 1/2 seconds. Okay, so after 1/2 of a second, the ball is at its maximum height. What is the maximum height? So we're going to evaluate the function at 1/2. So we have -16 times 1/2 squared plus 16 times 1/2 plus 96. So we have -16 times 1/4 plus 8 plus 96. So we have -4 plus 8 plus 96. So -4 plus 8 is 4, plus 96 is 100. So the maximum height of the ball is 100 feet off the ground. Still working with the same function, letter D, after how many seconds does the ball hit the ground? So there we're looking for our x-intercept. So we're going to set the function equal to 0. So we can factor out a -16, t squared minus t minus 6 equals 0. We can factor this quadratic, t minus 3 times t plus 2 equals 0. So either -16 equals 0, t minus 3 equals 0, or t plus 2 equals 0. So -16 does not equal 0. Here we have t equals 3, here we have t equals -2. Now that brings in the conversation of an appropriate domain, something we've discussed before in this course. If we're measuring t in seconds and we're modeling the height of the ball above the ground, it doesn't make sense for t to be negative, right? So if we were going to state a domain for this problem, it would be some domain where t is greater than or equal to 0. And if we want to go even further, we know the ball hits the ground at 3, and then we'd stop measuring the height. So if we want a really accurate domain, we would say the domain is 0 to 3. As an inequality, 0 is less than or equal to t, which is less than or equal to 3. So because of this understanding of an appropriate domain, t equals -2 doesn't make sense in the context of the problem. So after how many seconds? The ball hits the ground after 3 seconds. And then what is the average rate of change of the ball on the interval 1 to 3? So remember, this is a t interval. We typically thought of this as an x interval, but remember the variable is changed in this function. So 1 is less than or equal to t, which is less than or equal to 3. We know at 1, the height of the ball was 96, and we know at 3, the height is 0. We just found that. So we're finding the slope between those 2 points. So 0 minus 96 over 3 minus 1, which is -96 over 2. So our slope is -48. Hey, and if we want to put a unit here, it would be feet per second. Okay, feet because that's the y, right? The h of t, that's the measurement of the y, and seconds is the measurement of the x. Slope is change in y over change in x. Next example, a model rocket is launched straight up into the air. The height of the rocket is represented by h of t equals -16t squared plus 64t, where h of t is the height of the rocket in feet, and t is the time in seconds since the rocket was launched. Part A, how high above the ground is the rocket after 3 seconds? So we're going to evaluate h of 3. So -16 times 3 squared plus 64 times 3. So we have -16 times 9 plus, we'd have 180 plus 12, 192. -16 times 9 is -144 plus 192. That's going to be equal to 48. So how high? 48 feet. After how many seconds did the rocket reach its maximum height? So in order to determine that, we're going to find the axes of symmetry of our quadratic function. So t equals -b over 2a. So t equals -64 over 2 times negative 16. So we can simplify. So negative 16 and the negative 64 would be positive 4 in the numerator. So 4 divided by 2 is 2. So 2 seconds later, the rocket is at its maximum height. What is the maximum height of the rocket? So we're going to evaluate h of 2. So we have negative 16 times 2 squared plus 64 times 2. Just make sure I had that correct. Negative 16 times 2 squared plus 64 times 2. So we have negative 16 times 4. Fix that 4. Plus 128. Negative 16 times 4 is negative 64. Plus 128 is positive 64. So 64 feet is the maximum height of the rocket. Still the same problem, part D. After how many seconds did the rocket land back on the ground? So we're looking for the x-intercept, or the x-intercepts. So we'll set negative 16t squared plus 64t equal to 0. We can take a greatest common factor of negative 16t out. That leaves us with t minus 4 equals 0. So either negative 16t equals 0 or t minus 4 equals 0. So t equals 0 or t equals 4. Now the key here is after how many seconds did the rocket land back on the ground? So it landed back on the ground after 4 seconds. We found t equals 0 because this rocket also started on the ground. If we were to sketch the path of this rocket, it would start at the ground, it would go up to its maximum point, and then back down at 4 seconds. And that would be that vertex at 2, which we found on the previous slide. On what interval was the height of the rocket decreasing? Okay, so interval, we're talking about a time interval. So t values. Well, sketching out the height of the rocket above the ground with relation to time actually helps us here. The height of the rocket is decreasing from time 2 to time 4. So we'll say from 2 is less than t, which is less than or equal to 4. We could also say 2 is less than or equal to t. Both would be acceptable answers here. Okay, so or 2 is less than or equal to t, which is less than or equal to 4. And we can write this in interval notation as well. Parenthesis 2 to 4 with a bracket. This would be bracket 2 to 4. The reason both are acceptable is some people include that vertex point as being decreasing, and some treat that as a neutral point, where the rocket would be neither increasing nor decreasing. So it's a matter of how you interpret the problem. Part F of the same example, when was the height of the rocket 48 feet above the ground? So now we're setting negative 16t squared plus 64t equaling to 48, because 48 is h of t, a height. Now in order to solve this, we need to set it equal to 0. I'd like this to be a positive 16t squared, so we'll move our terms to the right. So 0 equals 16t squared minus 64t plus 48. I'm going to move the equal 0 to the right side, just so it's more traditional. We can take a greatest common factor of 16 out, and we'd have t squared minus 4t plus 3. So we can factor our trinomial. T minus 3 times t minus 1 equals 0. So either 16 equals 0, t minus 3 equals 0, or t minus 1 equals 0. 16 doesn't equal 0. T equals 3, or t equals 1. So 1 second or 3 seconds. Both of those are the time where the rock would be 48 feet above the ground. If we went back to our diagram, looking at the height, right? The y is the height, x is the time. 48, that's going to be there and there at 1 and 3. So it hits that height on the way up to the maximum point and on the way down. That's why we found 2 t-values. Our last example, a baseball is thrown straight into the air, released from a height of 7 feet above the ground. The baseball's height is given by the function below, where t is measured in seconds. So the function is h of t equals negative 16t squared plus 64t plus 7. After how many seconds to the nearest hundredth does the baseball hit the ground? So when I see this in a problem, that tells me it's probably not going to be factorable, and we're going to have to use the quadratic formula in order to solve. So looking for when the baseball hits the ground, we're setting negative 16t squared plus 64t plus 7 equal to 0. And we'll set up the quadratic formula. So a equals negative 16, b equals 64, c equals 7, and our discriminant is b squared. We'll do it over here, b squared minus 4ac. So that's 64 squared minus 4 times negative 16 times 7. 64 squared is 4,096. And then plus 4 times 16 times 7 is 448, giving us a discriminant of 4,544. So quadratic formula, x equals negative b, so negative 64, plus or minus the square root of the discriminant, 4,544, over 2a, so 2 times negative 16. So we have x equals negative 64, plus or minus the square root of 4,544 over negative 32. So we'll split this into the two solutions. So x equals negative 64 plus the square root of 4,544 over negative 32, as well as x equals negative 64 minus the square root of 4,544 over negative 32. So we'll check this solution first. So we have negative 64 plus the square root of 4,544. Now that's a positive number, and if I divide it by negative 32, I would get a negative number, so I'll stop there. We're going to reject this answer because it will be negative. Right? In the context of the problem, it doesn't make sense. We don't have a negative time where this hits. And actually, looking at my work, good thing I caught it. These aren't x values in this particular problem, so let's change those quickly. That's going to be t, 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 and t. Now back to the calculator, let's check this solution. So we're going to take negative 64 and subtract the square root of 4,544. And then we're going to divide negative 32. And we get 4.1065. So 4.1065. And that decimal keeps going. We're rounding to the nearest hundredth. So 10th hundredth. So that's approximately 4.11 seconds that it takes for the baseball to hit the ground. Okay, so wouldn't it have been terrible if I had it as x instead of t? No, we would have still got the answer. But I want to make sure that we stay consistent to the variable in the problem. And in this particular example, we couldn't factor the quadratic. So in order to answer the question of when it hit the ground, we used the quadratic formula. So this video is really about taking all of the pieces of a quadratic function that we found to graph the parabolic curve and applying them to projectile motion. So that's the axis of symmetry, the vertex, the y-intercept, the x-intercept. And from there, the context of the problem changes. Whether we're throwing a ball or launching a rocket, similar computations, slight variations in each problem. So the best way to get used to those variations, do as many problems as you can until you're confident with the material. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.